Okay, so we've got another question here about this thing called the Haber process. Lovely diagram here showing you what's going on with the things going in, reactor, blah, blah, blah. Then it says we've got a mixture of gases, and then we've got some boiling points somewhere. Looks like it's over here. There we are. And it's saying, how can you separate the ammonia? Right, so what have we got? Well, we've got the ammonia has clearly got the higher boiling point of these. So if these are all gases, if you cool them down, and that will probably get you a mark. So cool down this stuff to a temperature that is, well, basically between minus 34 and minus 195. So I guess, why would you call it any lower than minus 34? Then the ammonia will condense, so you can take it off. So cool down the mixture to what did I say, about, probably shouldn't say about, should I? It's a bit of a vague thing to say. Let's be specific. To minus 34 degrees C. Just call it down is not good enough, because if they have given you numbers, this is quantitative stuff here. If they've given you numbers, then you really should give numbers in your answer. I guess you could put minus 33, but just to make the point, I mean, it's got to be below that really. So minus 34 looks like a decent thing to go for. Right, what happens to the unreacted hydrogen and nitrogen? Don't know, let's have a look. Well, there we go. Nitrogen, hydrogen reactor. That's where, oh, here you go. That was a bit of a clue as to what happens, wasn't it? So there's the condenser. Right, and then look, there's an arrow here. So it's going back round. So in terms of how we're going to write that, probably the easier thing to say is that it is recycled. Spectacularly badly wrong, which is relatively hilarious. Let's try that instead. So recycled round to the reactor, as it says in the picture. Right, then you've got a lovely equation here. Oh, nice. Calculate the volume. Right, okay, this is proper synoptic stuff. So this is back from calculations. So what do we got? From the complete reaction of 825 decimeters cubed of hydrogen. So that's 825 dm cubed. And I want to know how much of that we've got. Right, okay, so this one, what they are looking for you to realise is that 1 mole of gas occupies 24 dm cubed. Where on earth did I get that from? Well, you just got to know it, I'm afraid. So what that means is, if I work out my number of moles here, I can just do, what if I've got 825? It's going to be 825 times 24 if I want my number of moles. And if I look at my ratio, I've got 3 moles makes 2 moles. So I've got 3 to 2 ratio. So what am I going to have to do to that number? Well, I'm going to have to divide it by 3 times it by 2, because I've got 3 to 2 ratio. So I'm just going to write that here like this. Divide by 3. And then times by 2. And that will get me the number of moles of ammonia. But then I want the volume of ammonia. So I'm then going to have to divide that by 24. Now, what that means is essentially I'm multiplying by 24 and then dividing by 24. So I could essentially not bother to do that if I didn't want to. So what does it end up with? Well, it ends up being 825 divided by 3 times by 2. Yep. If you are unhappy about that, then feel free to lob the 24s in. So times by 24 and then divide, but you're just doing the same thing twice. So if you plug that in, that gives you 550 decimeters cubed. There are 2 marks here. What do you get them for? Good question. You get 1 mark for realising that the ratio is 3/2. Oh, sorry, the ratio is not 3/2, 2/3. So you divide by 3 and times by 2. So if you've done that, you get 1 mark. And the other mark is for basically getting the right answer. Okay, is there more of this? There is. Where's the next bit? There it is. Okay, so there we go. Why are we using conditions of 450 and 200 atmospheres? Good question. Why are we using that? You've got to tick 2 boxes. Hopefully you've done that. The Haber process. 200 atmospheres, of course, is a high pressure. So a low pressure would decrease the yield. You need a high pressure. Why? Well, because if you look back here, it's the old molecules thing again. 2 on this side, 4 on this side. So therefore, a high pressure is good for the yield. So a low pressure would decrease the yield. So that's one of the reasons why you're doing it. Now, the other thing is, the reason they're running it at this temperature, even though the forward reaction is exothermic. So if the forward reaction is exothermic, that of course means to get the highest yield, you need a low temperature. That's not a particularly low temperature. So therefore it must be something about rate somewhere. Where are we? There you go. Lower temperature would make the reaction too slow. Okay, then let's have a look at this one. Lovely table of, what's this? Fertilizers, beautiful. Which element in compound A improves agricultural productivity? Okay, so this is just a learn it. You should know this really. It's good old nitrogen. 2 compounds going mixed to make a fertilizer containing all 3. Okay, so what are they getting at here? They are getting at the fact that you should be aware that those are your magic 3 elements: nitrogen, phosphorus, and potassium. All right, so therefore you're going to go with B and C because we're only allowed 2, so you can't just lob them all in. All right, and the reason, of course, is because of what I just said. So they contain nitrogen, phosphorus, and potassium. Right, okay. Then we got a figure 2, which I currently don't have. Where's that? Next page, yes. So here we go, where's figure 2? Oh, nice. Right, so there's me figure 2. All kinds of jazzery going on here. What's all this about? 2 possible reasons for the difference in cost between B and C. Right, okay. So, that's it. Fertilizer C. Fertilizer B, we've got all kinds of jazziness going on. All right, so therefore, the fact that B has more stages to the process is going to make a difference to the cost. Basically, the more stages you have, the more likely it is that it's going to be expensive. So the other thing you might want to look at is you've got 1 starting material here. 1, 2, 3. So B has more raw materials being things from the start. I guess you could say starting materials. You could also imply that it uses more energy because there's more parts to the process. You could also, I guess, imply that it takes longer because there's more parts to the process.